some not so great properties of code corpuses, I hope to end this session with a more positive note on how we can benefit from a large code corpus. So my name is Sifei Luan, and this is my colleague Celeste Barnaby. And together we're going to present our work called Aroma. It is a code recommendation tool we built, and it does it with structural code search. This is joint work with also Di Yang from UC Irvine, Professor Koushik Sen from UC Berkeley, and then our team leader Satish Chandra, who created the Big Code team at Facebook. So a little bit of our team, we are called the Big Code team at Facebook, and what we do is we do software engineering and machine learning research, and also build tools to improve our developers' productivity. So outline for this talk, we'll give a little motivation of why we built this code recommendation tool. We'll show a little demo of how it works, and then we'll go into details of how the Aroma algorithm works, and then evaluation of how well it works. So let's start with a scenario of a modern day developer. So modern day developers mostly work with just tons of APIs and frameworks. So imagine you're an Android developer, let's say at Facebook, and you're given this task to just load a bitmap and then to put it on the screen. So you look up some documentation, maybe you go to Stack Overflow, and they came up with this line of code, which you find is pretty easy. Just in Android framework, there is this bitmap factory method and class, and it calls a decode stream method and just decodes a bitmap. So great, you're all done, right? That was easy. Apparently that's not true. And why? Because this line of code that you write, if committed and deployed, will run on millions of devices across the world on all different kinds of phones. And what that means is that you really want to make sure that this line of code does what it does and would not just crash if something wrong happens. Maybe that means you need to add additional checks, safety checks, guards against some exceptions in case memory goes wrong, the device goes wrong, something like that. In other words, after you write this line of code, there's a second question in mind, which is, what else should I add? And this is not such an obvious question from like a Android framework documentation, because it might not tell you everything. But what can we do about it? Well, the good news is we're working in a big code corpus. That means, well, for some task like just loading a bitmap, you can imagine that there's someone already doing something like this very similar and exists in the code base. What we need is a way to automatically find these positions and to see what we can get from them. So to support the claim I just made, we actually did an experiment where we took a set of new code changes committed by our developers from the past week, and then we also checked if these code changes actually resemble some part of the code that already exists in the repository. So in other words, there's this question of, is new code really new? And we have details in the paper about the experiment. But the short answer is, well, it's pretty surprising. Almost 1/3 of the new code is actually not so new, which means we actually found some level of syntactical similarity between the new code and some existing code in the corpus. So what does this tell us? Well, this is not about clone detection, but more of an opportunity that we see where we can benefit from this kind of similarity. We can find the code that's similar to this new code that we write, and we can see how we can build ways to let the developer benefit from it. And this is precisely what we have built, Aroma. So now let's see a quick demo of Aroma using the same example of the bitmap loading example that we saw before. I know it might be a little small, but we will show the contents of the screen in the later slides. So let's go back to the developer. Let me play this. Let's say you write this line of code and you now want to say, what else can I do? Well, so you just hit a hotkey, and then immediately you start seeing this stream of code recommendations on the right-hand side, the popping with the code that you just wrote. And what these are clustered code search results that Aroma found from the code base, and they're clustered together so that they can provide examples of what other code can be added to your current code. And the developer can browse through this code and maybe they find something useful and they can add it to their own code. So let's come back to the example of the bitmap loading. What are the kind of the code recommendations we can get from a big code corpus? For the purpose of this demonstration, we did not use the Facebook Android codebase, but rather we took a collection of a large sample, about 5,000 Android projects from GitHub. We did deduplication and all of that stuff. So here are the results. And also, I think it's worth mentioning that Aroma did not come with any assumption of what kind of thing they're looking for. They're just purely searching for code and trying to come up with recommendations based on these. So let's take a look at this first recommendation. So here the highlighted 2 lines are the recommendation, and the 3rd line is the code that's found to be similar to the code that's being written. So in this cluster of 5 methods, we found a additional option called which sets a sample size, and is always passed into the decode stream method. What this actually does is that it would greatly reduce the memory consumption while loading a large bitmap. So maybe it is something that could be helpful to us because we want our code to make sure our code to run even on some smaller devices. So here's another example. This one is about the input stream and also how people remember to close that input stream after after opening the file. This is again just found by Aroma in a cluster of 6 methods, and it shows that it is idiomatic to close the input stream after use. So here's one more. In this case, in a cluster of 4 methods, Aroma finds that people wrap this decode stream method in a try-catch block, and it catches this I/O exception that could arise when you decode bitmap. And this is really important to us because this means that if we want our code to run and not just crash in case some file fails to open, we should also add this block. So these are some examples we have seen about what Aroma can provide as code recommendations. And now let's take a quick look at how Aroma does it. So here's how we formulate the problem. We assume we're given a large code corpus. In this case, in the experiment that we did, we took a sample of about 5,000 GitHub Android projects, and they sum up to about 2 million methods. And we're trying to find useful things from it. And we try to find these useful things based on the query call snippet, which is the code that the developer just write. So what are the goals? Well, first, we want to find all of the code in this big code corpus that are similar to the query code. But we do not want to show all of them because they can be plenty. But we want to show only a few representative extensions to the code snippet, which we call code recommendations. So there's a few key ideas I want to go through. The first one is called feature-based search. Basically, the idea of feature-based search is that we first need a way to reduce the set of 2 million methods into a much smaller set, which we can manage to perform more fine-grained analysis. And we need to do this in a reasonably fast way, so it's actually practical to use. So the idea here is that we want to extract a bunch of features from the left-hand side, which is just a piece of source code, into we want to extract those features, and then we want to turn them into a vector, in this case of one hard encoded feature vector, and then we can perform fast search on this code vector, and then to get the results that we need. So how we do this is that we just take the source code first and take it through the Java parser. In this case, the sample code is in Java, and then get this generic tree form that we use to extract features. So this is the only step that is language dependent, in the sense that if you want to do Aroma for other languages, so in our experiment we did also Python and Hack and JavaScript, we just need this parser to turn code into parse trees, and then the rest of the algorithm is pretty much language agnostic. So what exactly features do we take? The first kind is just we call token features. So this is just simply we want to take all of the identifiers, the literals from the source code and just extract those names. One thing we do is that for local variables like those I and VO over there, we replace the name with a little hash var thing indicating it's just a variable. The reason we do that is we want to make sure that, because people use different names in their local variables, we want to capture their meanings using other features, but not focus on their names. So the second, now from the second category is all structural features. These are called parent features, and what these are is that there's a way to capture basically how a variable is being used, where is it being used in the syntax tree. So for example, here this view variable is being concatenated with its parent node, grandparent node, great grandparent node, and then so for example, this one feature means that this variable is being used in a casting expression, and then it's also being used in a method selection expression. So another example, for example, this loop variable I, although we discarded its name, we put it in this, we get this feature so that we know that it is in the right-hand side of assignment, and it is also an int, and it's being used in a for loop. Now the third kind of features are what we call sibling features. Now what these are is, well, because after we take all the features, we just take them pretty much as a set, so we lose the actual ordering of those nodes. We want to capture the local ordering and what their neighbors are, so we just simply take the neighbors of the node in the syntax tree and concatenate them together as sibling features. And the last one are variable usage features. So here we want to convey the idea of, for example, the return value of function A gets passed into this function B, and so on and so forth. So what we do is that for every occurrence of the same variable view, we take the parents and then we concatenate their parents as a feature. So for example, the name view is discarded, but we'd say that the thing that's used in the instance of expression is also later being used in the casting expression. So after we take all these kind of features, we do this for every token in the syntax tree, and then we do this for every method in our code corpus. And then after that, we can collect a large, will be a large set of all possible features, and we simply assign a unique index to each of them. And then we can create, for every code snippet, for every method in the code base, we can create this very long but very sparse feature vector that basically this feature vector itself represents all of the features we need from the source code. So from now on, we can simply concatenate all of those feature vectors into a big feature matrix. And then when we want to search for a piece of code, we simply do the same thing for the query code. We take its syntax tree, we take its features, we turn it into a vector, and then we multiply this matrix with the sparse vector, and what we get will be, and then we rank the resulting list by the dot product, and then what we get will be the methods that contain the most number of overlapping features, which are the similar code that we want. So the reason we do this step is because this can be implemented actually very fast in parallel. So for example, for the code corpus, it actually takes less than a second for over 2 million methods to find the most similar code. Now, so this will reduce the set of like 2 million methods into maybe 1,000 methods on which we can perform more fine-grained analysis. I'm gonna turn over to Celeste now.
Cool, thanks. So moving along, we now have this list of the 1,000 methods that have the most overlap with the query. So the next step will be to re-rank and cluster those methods. So re-ranking is important because it gives us a more precise measure of similarity. For instance, given the query on the right, the method on the left may be one of the top search results, but we want to know how much of the query is contained within the method, not just how much overlap there is between the two. That is, we want to be able to identify and isolate the part of the method that most closely matches the query. So in order to do this, we define a similarity score between a query Q and a method M with this formula. So here, Q and M are both parse trees, and there are a couple things about this formula that make it more precise than the overlap score. First of all, notice that we're looking at the feature sets of the query Q and the method M. These are the multi-sets of the features that are extracted from the query in the method, which means we're looking at not just whether or not a feature is present in the method and query, but actually how many times it appears. And then also notice that we're looking for the subtree M prime of the method M that maximizes this similarity. We call this process of finding the subtree M prime pruning the tree, which we do with the greedy algorithm. So this measure of similarity is more precise than the overlap score, but finding it is also more expensive, which is why the feature-based search from the last phase is still important to narrow down that corpus of millions of methods to just 1,000. So now that we have this measure of similarity, we can simply calculate the similarity scores between the query code and each method in our list. which gives us a list of the most similar methods. But this would still be like way too many methods for a user to actually look through. So the next step will be to cluster those methods. So remember that the overall goal here is to create code recommendations, which we're going to do by intersecting the methods in each cluster. So with that in mind, um, our clusters need to have two constraints. The first is that when all the methods in a cluster are intersected, it should produce a code snippet that extends the query. If a code recommendation is like the same length or shorter than the query, that's probably not going to be very helpful. And then second, all the methods in a cluster should be similar to each other. And this is because we sort of want each recommendation to represent a single code pattern. So with that in mind, we found that common clustering algorithms that already exists didn't really produce good results. So we designed a custom clustering algorithm that satisfied these constraints that works as follows. So we start with each method in its own singleton cluster, and then at each iteration for each cluster, we find the best snippet to add to the cluster. By best, we mean sufficiently larger than the query and most similar to the other methods that are already in that cluster. And then we iterate until all the clusters stop changing. And then finally, we get rid of all similar looking clusters, by which we mean having a Jacquard similarity of greater than 0.5. We don't require our clusters to be just disjoint, so the same method could appear in multiple clusters. So now that we have this much shorter list of clusters, the final step will be to intersect the methods in each cluster to produce our short list of recommendations. At a high level, intersecting works by first taking the first method in a cluster and comparing it with the second method in a cluster. When we compare these two methods, we preserve code that is found in both methods, and we remove code that is unique to a single method. So here you see we remove a couple of lines of code that are only found in the base method, and we keep the lines that are found in both methods. We then compare the base method against the third method in the cluster and repeat this process. So here now we removed another line of code from the base method that is not found in the third method. And we repeat this process of comparing the base method against every method in the cluster until we get our final code recommendation. So now that we've seen how Aroma works, I'll talk a little bit about some of the evaluations we've done. So to evaluate the quality of Aroma's recommendations, we went to Stack Overflow because of its wealth of coding questions and answers. And for this experiment, we picked the 500 most popular questions on Stack Overflow with the Android tag and looked at the top voted answers. Answers on Stack Overflow, especially top voted ones, usually contain a code snippet representing a useful or popular coding pattern. So from each of these answers, we extracted those code snippets that had at least 3 tokens, 1 method call, and fewer than 20 lines of code. And then we randomly picked 64 code snippets from this set. This is an example of one of the code snippets we extracted. It shows how to hide a soft keyboard in Android. For each of these snippets, we manually created an Aroma query by taking the first half of the snippet. For instance, this is the query we extracted from this snippet. And since this code snippet likely represents a popular coding pattern, we wanted to see if we could give Aroma this query and if it would recommend the rest of the code snippet. That is, if it could tell us that if this is our code, then we should also add this code. So we couldn't extract code snippets from 14 of the 64 full code snippets because they only contained one statement. But for the remaining 50 code snippets, the Aroma results fell into one of two categories. So in 74% of cases, one of the top 5 Aroma recommendations was an exact match to the full code snippet. whereas in the other 26% of cases, none of the top 5 Aroma recommendations matched the snippet and instead offered an alternative recommendation. So if we go back to the query we were looking at a second ago, this is the code that Aroma recommends, which was created from a cluster of 3 methods. So here, the highlighted code matches the query, and the code above and below the highlighted line is the code that Aroma recommended. So here, the recommended code, if you look at it, you'll see that this is an almost exact match to the code in the original full code snippet. We also ran Aroma searches using the full 64 full code snippets as queries to, again, look at the quality of Aroma's recommendations and see if, basically, if Aroma thought there was anything else we should add to these code snippets. We classified the recommendations into the following 5 categories. The first 4 categories here describe extensions to the query code that improve the quality and functionality of this code, such as configuring objects, additional error checking and handling, etc. And the final category describes the rare case where all the methods matching the query snippet were mostly different from each other, so Aroma was unable to perform the clustering and intersecting steps. But for 92% of the queries, Aroma generated at least one recommendation that we found to be useful. So to summarize, 1/3 of new code we found contains meaningful similarities to code that already exists in a large code base. And so Aroma can help developers to identify and utilize this similar code to save time and energy. And in our experiments, Aroma was able to provide exact recommendations for 74% of Stack Overflow questions. So our paper can be found at, and paper artifacts can be found at these links provided. We will be at the poster session tonight, and we are working on a public demo website where you can try Aroma out for yourself. That will be coming soon. And that's it. Thank you.
Thank you for demonstrating cool feature. One problem with Stack Overflow code snippets, they have bugs, or sometimes they can introduce bugs because people don't understand what they have copied. How does Aroma solve this problem?
So if I understand the question correctly, is that if Aroma found buggy code in the corpus, how do we deal with it? That's a good question because, well, honestly, when we designed Aroma, we assumed the corpus it operates on is the production code base, which hopefully is more or less the idiomatic, the correct code. Although, yeah, you can argue that that's not true anymore, and that's kind of the thing that we find. So I guess one obvious thing that we found, we actually rolled this out as a feature, and we found that sometimes people complain that you actually recommended deprecate code from the code base. Not necessarily wrong, but it's deprecated. So we're also working on a way to maybe find signals with code that's outdated or it's potentially buggy and try not to recommend those.
Thank you.
Hi, good talk. Maybe my question is related to the previous question. Have you seen this paper from Millian Kim's group from UCLA in XC18, I think, which is about how good the code examples on the online forums are? Have you seen the paper?
Yes, we have seen that paper.
And then what's your take on using that code?
You mean using the code from the online forums?
Yeah. I think it's a very interesting tool you have. Just, I guess there's an assumption about the goodness of the code, right?
Yeah, I understand. I guess one thing is that we try to provide an alternative approach, whereas obviously on the one hand, if you have Stack Overflow, that's great, and Stack Overflow has the question that you have in mind, then that's great because people provide good examples. On the other hand, let's say you work with a language that's not on Stack Overflow, or you work with a framework that's not Stack Overflow, which is pretty common actually in companies. Aroma provides a way of generating these examples strictly from the code base rather than relying on some external examples. But yeah, it would be a good idea to, for example, for the open source Java Android, it would be a good idea to try to integrate those.
So question, so you're using a mostly syntactic feature of the language, but I also assume that if you have similar API function or similar text, it will also be a very good recommendation. Did you try to use a standard text search to find good recommendation that are similar text?
Yeah, so I think that's fair. For now, we stuck with mostly syntactical features because one is pretty more, it's more straightforward to examine that these are the exact APIs to recommend. Similarities of APIs or functions is less well defined. So we did think about using, for example, some textual analysis on the API names to see if some things are similar. But for now, we stuck with, for this approach, we stuck with just the exact names.
Hi, so you evaluated your approach by testing on the Stack Overflow questions. You can assume that the corpus contains some copies of the exact answers from Stack Overflow. Did you account for this dependency?
So it is, on the one hand, possible that the corpus contains some code that's directly copied from the Stack Overflow. It is also possible for the corpus to not contain anything because I mean, in the end, these are kind of fabricated code from people. So that's why I guess in the end we did not say like the recall was some percent or something like that, but rather we try to categorize what kind of recommendations Aroma provided and just leave it like that. So yeah, we do not have the ground truth per se.